Okay, so hi everyone. Today I'm going to be talking about the aspect Fastscape coupling. And so this is a coupling that allows surface processes to be used with aspect models. And so generally now when you use aspect, you use a free surface, which allows the surface to deform based off of these tectonic forces. And one of the issues with this is that you can get very high or unrealistic topographies, either high mountains or low valleys within the model. And this is because there's no erosion or sediment deposition to redistribute the surface through time. And so if you can have these surface processes that changes the surface, you actually change the loading at the surface, and also you can have some small effect on the temperature. And so there's a few different ways to do this. One is to use a diffusion equation, which is a short-range transport of sediment, which you can kind of see an example up here. And this is something that can be done with the mesh deformation aspect as of now. The second is to couple a tectonic code like aspect with a dedicated landscape evolution code. And here's an example here with ones like Underworld or Fastscape. And so this just allows a few different ways that you can additionally deform the surface. And so at least for rift models, one of the things that previous work has found is that when you have surface processes, you actually increase fault localization and prolong fault lifespan. And so to go a little bit into what Fastscape does, it's a landscape evolution code that has a few routines that form the surface like a sedimentation erosion. And over here, you can see the erosion away of a mountain. And so this is an open source code that's available in quite a few different languages. The coupling that I'm talking about today is coupled to the Fortran version, but Mikhail Pons is currently working on also coupling this to the C++ version. And so to talk about what Fastscape will actually do to the surface, it depends on whether you're above sea level or below sea level. When you're above sea level, there'll be an uplift rate and an advection term. And so these are velocities that will come from aspect to Fastscape, which is also to say that we allow Fastscape to handle all the movement of the surface. Next is the stream power law, which is the long-range transport of sediment. So this is how we really incise rivers into the landscape, as you can see over here. And one thing I don't mention about this, the stream power law isn't inherently mass conservative. It assumes that there's some sink for the sediment that's held in these rivers that's often off model, but at least some amount of this can be deposited back onto the continent, as you can see down here, which would be from the sediment deposition term. And then lastly, there's that short range transport of sediment through this hill slope diffusion. So if we then go below sea level, it's pretty similar with some differences. There's again the uplift rate and advection that we would get from aspect. There's then this marine diffusion term that's similar to the hill slope, but in the marine setting. And then after this, there's this continental sediment flux. And so what this really means is that if we have an ocean in our model, this would then become the sink for all our sediment. So all the sediment that's held in the rivers from the stream power law can now deposit into this ocean. And then lastly, we just have this background oceanic sedimentation rate that you can add in models if you desire it. So to talk a little bit about how it works, it depends a little bit about which time step. So on the first time step, the first thing that we'll do is we'll get the height and the velocities from aspect, and we'll send these to and use them to initialize Fastscape. Once we have this, we'll save this initial surface, and then we'll run Fastscape with all these routines. After this, we'll compare the difference between the new surface and the initial surface and divide it by the aspect time step to get a Z velocity for all these locations. And then we'll use this to update the aspect surface so that it matches what Fastscape has. On other time steps, it's pretty similar, but there's some small differences. The main one being that the height is no longer sent and we just send the velocities from aspect. And this is because Fastscape will often be at a higher resolution than aspect, and we don't want to lose this resolution from including the topography. But after this, it'll go through the same process of updating Fastscape, getting the change in velocity from the two surfaces, and then updating aspect surface. And so things that you can do now with this coupling is all those things I talked about, like the stream power law, marine processes, these can all be included in the models, and they can be applied to 2D or 3D models. In the case of 2D models, you just pick the length of your Fastscape in this direction, and then it'll take the value from aspect and copy it to all these nodes along strike. And then after you get the velocity along all these, it'll average them together back to send to aspect. Let's see. Yeah, and so again, as I said earlier, we allow you to refine Fastscape above aspect. This is especially important in 3D models, where generally you want your Fastscape resolution to be about 1 kilometer or less. And then kind of on a similar note, Because aspect has different resolutions that it can appear at the surface, we wanted this to work with Fastscape as well. So if you know the maximum resolution of your Fastscape surface and the difference in resolution levels at the lowest one you expect at the surface, we can create enough interpolation points between this cell so they can still fill out the Fastscape mesh. And then the last thing is that Fastscape will write its own start file, so you can restart Fastscape with aspect and still keep this higher resolution. So with that out of the way, I just wanted to show a few examples, very broad examples to show this in action and answer a few questions like, can these surface processes actually have a large effect on 3D geodynamic models? And what kind of comparisons can we then make with nature with these sediment that we're now having? And then just a very quick look at some preliminary work I'm starting on with 2D subduction models. So for large scale 3D models, I first want to talk about models that I ran that had a free surface. And so this was just to see how two rifts interacted and connected. And what we found is that if you have a different strike perpendicular offset, you get different connection types, which could be, if they're close together, an oblique connection, farther apart, a transform connection, and even farther apart, they actually overlap and rotate the center to form a microplate. So when we were first testing this coupling, just to see if it works, we took this transform connection model and we put the Fastscape on top of it just to make sure things were looking correct. Where's my play button? So this is that model showing just the Fastscape surface where we initially have this rift flanks being formed and eroded into this marine setting that would be our rift valleys. And over time, we can see that these are propagating forward. And from the free surface model, we would expect that they would connect through a transform fault. But what we actually end up seeing here is that they begin to actually overlap and enter into this microplate regime instead, where we're just overlapping and rotating the center. And so just to really illustrate this, here's two of the exact same models, one with the free surface and one with the surface processes. And as we can see, this actually changed how the model ended up. Although I will say that this was just a test, so we didn't really have the most realistic parameters. There wasn't a dedicated sediment field or anything like this. So this might be overestimating the changes. But if you're interested in something like this, there was a recent paper from Wolf et al. 2022, where using a similar coupling with P. Tatton, they looked at how these rifts can connect. So the next question I wanted to look at was, what kind of comparisons can we start to make with nature from this? And so for this, I want to focus on the passive margins of rift, where generally you will have this history recorded in this crustal and mantolithosphere thinning and deformation. And so since we have surface processes, we can actually begin to see, we can fix the surface so we can start to see where we're depositing sediment and also the age of this sediment. And so then if we were wanting to compare this to actual seismic data, here's an example from Boyder et al. 2023, where they're looking at the Norwegian margin. And so if you look at the seismic data, they can see again the thinning crust and mantolithosphere that we could look at generally with the free surface, but also there's large amounts of sediment that they can see the structures and thickness as well. So when we add these on and we can start depositing the sediment, we can get an additional comparison with this seismic data. And similarly, if we start to look a little bit closer at these sediment structures that we're forming, because we're tracking the sediment age through time, we can actually see the orientations of these basins and how they change. So with this, we can see things like this angular unconformity, where we had older sediment that was broken off, tilted, and the new sediment was deposited on top of it, or these rift unconformities, where we had basins that formed during active rifted that were then inactive and overlain by older or newer sediment. And then even ones where we have large gaps in deposition of sediment, like here, where there's 8 million years where we're not depositing sediment. And so, of course, the nice thing about having models is that we can see this in real time. So this is a nice video that Sasha made of this 2D model. And so I'll play it here. So we can see we're initially depositing a lot of sediment into our rift valley, where we have this large initial basin. And so over time, this begins to split as we start to enter into this rift migration mode. And you can see here where we're starting to form these active rift basins that are younging towards the left. And then so eventually here too, you can see that we had this initial rift basin that was then broken apart and we're depositing new sediment over it. And then you can see this will be rotated and we get that angular unconformity. And at the same time here, we're depositing this basin here that is creating those rift unconformities. And then so over here later on, we can see at some point, this outer rift begins to reactivate. So this starts to tilt the basin, and we're again, after 8 million years of no deposition, creating enough accommodation space to have, again, this huge unconformity that we're seeing in the, that we saw earlier, I guess I should say. And then as it continues, we begin to break up some of the sediment and distribute it along the rifted margin. And so the last thing I briefly want to go over is just some very preliminary work I've started looking into for EGU that I'm working on with Whitney Bear, Adam Holt, and Jonas Ruh. And so this is kind of to look at how sediment affects the subduction interface in these 2D dynamic models. And generally the idea is that sediment is rheologically weaker than what you would expect in the interface. And because of this, it should lubricate the interface and lead to faster subduction velocities. However, there's also a paper by Fritzi et al. 2022 where they find that this is true, but at the same time, sediment is much more buoyant. So when you include this buoyancy effect, you actually may slow down subduction. So the question we are thinking of looking into is how much sediment can we actually expect to get into the interface if we don't have any initial sediment in there? And also, what point does this buoyancy become more important than the rheological parameters? And so to do this, we set up a 2D coupled model that's about 4,000 kilometers long and a little over 1,000 kilometers deep, with a maximum resolution of about 500 meters in around the trench. And so here's just a very close-up where I'm just focusing on the accretionary wedge in the top of the interface. And so here we have the overriding plate, the oceanic crust in gray, the slab down here, and then there's 500 meters of just initial sediment. So if we start to play this, we can see that we build up some sediment along the trench, and we kind of start forming this accretionary wedge. And one thing I want to note is that our continent in this case is actually quite a ways from our trench. So we're actually not getting too much sediment to diffuse out here, although there's probably some. But at the same time, we're still getting a lot of sediment within our wedge. And what I think is happening here is you can kind of see once I continue this, is that as we tilt this, we actually rotate this upward, and then we're eroding this almost instantly because we have such high diffusion in the marine setting in this case. And this has been providing sediment to then go to the toe of the accretionary wedge, of which some of this is then being brought into the interface, which you can kind of see by this white contour. So yeah, here you can see where we uplift this packet, it's eroded, and we're putting sediment down here instead. And then over time, this is gradually getting deeper and deeper into the interface. And so that's mostly all I wanted to go over today. Just to conclude, this aspect Fastscape coupling allows sedimentation and erosion on these models. It's now available in the mainline aspect. And so the surface processes can affect surface loading and a bit the temperatures as well. And they also give some additionally sedentary structures that can be compared to geologic data. Thank you.
All right. And certainly one of the coolest aspect users I've known about. Very, very cool stuff. So we said that we're going to have questions at the end of the session. Derek, stick around. And then Fred, you want to go next? You ready? If
Can you hear me okay?
Now I can hear you. Yes, perfect.
Can you see any slides?
And we can see those too. Yes.
Okay. Sorry. So, hi everyone. I'm Fred Richards. Introduced myself a bit earlier, so I need to go over that. So, I'm going to be talking about how we can quantify mantle dynamic impacts on topography, sea level and ice sheet evolution, and with the focus, obviously, during this particular meeting on how we can do that with aspect in particular. And so this is work that I've been driving over the last few years, but there's many, many collaborators you can see listed on here who've been a really kind of key part of all aspects of what I'm going to show today. So I think the first application I wanted to show to you guys was how we can use aspect potentially to look at large, low shear wave velocity province structure. And so this might be new to some of you, but there are these two very large provinces in the deep mantle sitting on the core mantle boundary with relatively low shear wave velocity anomalies. So one beneath Africa and one beneath the Pacific. And for a long time, there's been a lot of debate over what these actually represent. Are they just large thermal anomalies? They certainly seem to be related to where you have plumes. Or is there a chemical aspect to them? So some little cartoon. Plume models that in where thermally dense materials are relevant to the sort of metallicity. So I set out to do myself, Harriet, Mark Hogarth, Sigurd and Paula Kuhlmeier was to try and look at a range of different constraints that we could use to try and work out which of these different sort of end-member models was most likely the LSVP. So we have a set of geodynamic constraints. So for example, roughly what the present day dynamic topography field looks like, mainly based on residual depth anomalies in the oceans. It's a bit more uncertain in the continents. And you can see straight away that, so if you just look at the longest wavelength component of that dynamic topography field, there's very good correspondence between the large low velocity provinces with these kind of black contours here, and where you get dynamic topography highs at long wavelengths. So we think that, on average, there's a long wavelength high associated with the large low velocity provinces. And also there's a kind of a classic observation, so going all the way back to 1985 that Brad Hager and Mark Richards made, that these large low velocity provinces also seem to be correlated with a geoid anomaly high. And that's kind of very clear. And one other constraint we can use potentially is core mantle boundary topography. Now, unfortunately, that is less well constrained. Different seismological models come up with very different answers to what the CMB topography looks like. However, we do know from VLBI observations roughly what the 2-0 component of that dynamic topography is. So the kind of excess ellipticity of the core mantle boundary. So it's wider essentially at the equator than it is at the poles. So we can use these constraints to sort of look at what the density structure of these provinces might be. And we can also look at a few slightly newer constraints. So these are Stoney modes, which are normal modes that are especially sensitive to core mantle boundary structure. And also there's been Harriet's work looking at semi-diurnal body tides. So these are sort of deviations from what you'd expect for a sort of symmetrical Earth structure in the body tide response measured by GPS. And these are sort of two papers by Paula Kuhlmeier and Harriet Lau that came out in 2017. And interestingly, they found slightly different things. So Paula ended up advocating for a light LSVP. So the bottom 400 kilometers of the LSVP was made of relatively low density material. Whereas Harriet found that to explain the semi-diurnal body tides, you needed relatively dense material in that same kind of depth range. So there seemed to be a bit of a discrepancy there that we wanted to try and sort out. And then the final constraint you can use is the fact that we have paleo shoreline deposits from various warm periods throughout the past. So here I'm showing you mid-Pliocene paleo shorelines from around Australia. And obviously these form theoretically all at the same time. They should all record the same global mean sea level. But what you can see is that if you look at their present day elevations, they're covering about plus or minus 100 meters of topography, which suggests that actually mantle dynamics beneath this region has really pushed these shoreline deposits up and down through time. And that's a useful constraint as well on not just dynamic topography, but how it has evolved over the course of the 3 million years since these deposits were formed. So the aim is really to kind of integrate all these different constraints to work out what might be going on down in the deepest mantle. So initially, we weren't actually using aspect, we were using a relatively simplistic approach using what I know as instantaneous flow kernels to predict how dynamic topography, the geoid CMB topography evolve as a function of density and viscosity structure. And what we did was we kind of split our models into these different layers. So 2 mid-mantle layers, 2 upper mantle layers, 2 lower mantle layers. And in the lower mantle, we were allowing there to be density anomalies within the LSVP regions, which we were delineating with a 0.65% velocity contour. And so essentially what we were doing was assuming different scalings between VS and tomography models in these different layers to get into density. and also playing around with different intrinsic kind of chemical density contrasts between the inside and the outside SVP. What we did was we calculated joint fit to dynamic topography, geoid, CMB electricity, and we did this for 5 different tomographic models, because obviously tomographic models don't completely agree on what deep mantle VS structure is. And we also looked at 3 kind of independently constrained viscosity profiles to understand how rheological structure might add some uncertainty as well. And so the thing that we found was that essentially you're looking here, so the thermal predictions are in the middle row here, and the thermochemical model predictions are on the lowermost row here. The thermal predictions, they can do a good job of fitting the geoid and an okay job of fitting the dynamic topography, but they predict far too much core mantle boundary electricity. If you compare that with the thermochemical predictions, you're again getting about the same geoid fit, actually slightly better in terms of variance reduction. Again, a slightly better dynamic topography fit, but it's marginal. But importantly, you can get these 2 good fits to dynamic topography and geoid while simultaneously fitting the core mantle boundary electricity well. And this was the result that we saw across all the different combinations of sort of input viscosity profile and tomography model we use. So these panels here are showing you kind of misfit to the geodynamic constraints. So red is bad fit, lighter colors is good fit. And what you can see is that if you compare this with the thermal models where we didn't allow there to be density anomalies in LSVPs to the thermochemical models where we kind of relaxed that assumption and let there be density anomalies down there, for every single one of these combinations, we're getting a better fit with the thermochemical models. And interestingly, what we find is that sort of on average, we're getting about, you need about a 2% density anomaly, but just confined to the lowest 200 kilometers of the LSVP to be able to explain the geodynamic observations. So that's kind of the fit to the geoid, the dynamic topography, the CMB electricity. But I also introduced some other constraints we can use, so Stoney modes and body tides. And so the interesting thing we found that's slightly differently to what Paola found in her initial Stoney mode paper is that whether you use a thermal or a thermochemical model, it actually seems to give you almost exactly the same fit to the Stoney modes. Some models it's slightly better for the thermochemical, but overall it's pretty even. So that suggests that Stoney modes don't necessarily answered in opposition to the idea that there's enormously dense material, especially if it's only confined very close to the core mantle boundary. And then we looked at the kind of body tide fits. Again, thermochemical models did a significantly better job. So what we concluded from this was that these thermochemical models where the chemical heterogeneity is confined just to the bottom 200 or so kilometers of the LSVP, that can resolve the Stoney mode and tidal constraint discrepancy with respect to LSVP density, and it also can reconcile all the geodynamic constraints. So we think essentially all these different pieces of evidence are pointing to the fact that at least the very bottom part of the LSVP must be made of enormously dense material, probably at least 2% more chemically dense than the ambient mantle. Kind of where aspect comes in is the other question I've sort of started to ask myself is, can we get any constraint on what the viscosity of this material is? So is this just kind of similar viscosity to ambient mantle, or is there a viscosity contrast between the sort of ambient mantle and the anomalous material in the bottom LSVPs? And to look at sort of viscosity variations, obviously you can't use an instantaneous flow kernel methodology where you just assume radial variations in viscosity only. And so then in these cases, I've turned to aspect to answer these questions. So I've sort of loaded in the density models that I got from the instantaneous flow kernel optimizations, and essentially looked at how the fit to these mid-Pliocene shorelines from around Australia, how that varies as you change the kind of chemical viscosity prefactor, so the kind of intrinsic viscosity of the material within the LSVP. And the interesting thing is that you find for sort of whether it's CMB misfit, geoid misfit, or dynamic topography misfit, you do tend to want an enormously viscous material in the LLVPs. In all cases, that gives you a better fit to both present day constraints, but also importantly, it gives you a better fit to the Pliocene to recent dynamic topography change inferred from these mid-Pliocene shorelines. So what we can say is that not only does this material seem to be dense, but it also looks like it's about a factor of 100 to 1,000 more intrinsically viscous than the stuff around it. It's quite interesting. So just to kind of summarize that, sort of that first outcomes of that first project so far, at least, is that we think to reconcile all this different data, we need the bottom part of LSVP to be anomalously dense, but also anomalously viscous. And that kind of agrees with the idea that these things might have been relatively stable over time and are quite hard to push around. So it's a sort of model approximating what is shown in the bottom right here. And why it's more viscous, that's still an interesting question that's open to interpretation. My view is it might be due to post-perovskite differences between the inside and the outside of the SVP, but yeah, definitely something to discuss. So that was sort of the first project. I'm going to try and see if I can talk about other things I've been working on in aspects without Wolfgang taking me off the mic. So the first one was,
you do have a couple minutes. All good.
Oh, thank you. So it relates to looking at mid-Pliocene sea level. So I already sort of introduced in the previous part how we have these sort of observations from around Australia that these shorelines are being pushed up and down by the mantle. And the reason why we want to understand mid-Pliocene sea level and kind of correct out that dynamic topography effect is that what sea level was during this time is quite a good proxy for where we might end up in the near future, because the mid-Pliocene had very similar temperatures to where we think we're going to end up, even if we do implement the Paris targets, and similar sort of CO2 levels, so about 400 ppm. And as you can see, there's a big uncertainty on the sea level during this time, but we think we lost large amounts of Greenland and also potentially a large amount of Western Antarctica. And what people have done in the past, so for example, there's this famous paper by DeConto et al., is they used a sea level constraint from the mid-Pliocene, tuned their ice sheet models so that they could kind of reconstruct this Pliocene sea level estimate, and then use that to then run their model forward in time to predict what would happen. And it's those kind of calibrated ice sheet models that give you these very scary projections of sea level change in the future, where, if emissions aren't abated, we could be getting up to 2 meters of sea level rise by the end of the century. So these calibrated models are suggesting we're going, the projections are even more scary in terms of future sea level change. So what I did was I've been looking at essentially running backwards advection models and aspects to look at how dynamic topography has changed through time over the Australian region. And so here's an example of one of these simulations that I run forward. But in the Australian case, there's two main things going on. So first of all, Australia is sort of rocketing northwards into the Indonesian subduction zones. But also you've got a lot of downwelling underneath Australia that's the continent is sort of moving over, and that gives you a quite complex dynamic topography field. So as I kind of run this forward, Australia is moving north, and also you're getting kind of downwelling flow underneath that region. And so if you take those original paleo shoreline estimates from around Australia, you can see that they're not actually forming like a nice consistent line as you'd expect, given the fact they all formed at the same time and should record the same sea level. However, if you then correct for both glacial ice static adjustment and then dynamic topography, more importantly, suddenly all these paleo shoreline estimates fall upon a nice clean line. And you can then read off an estimate of what sea level was during this mid-Pliocene period. And what we find is that in general, mid-Pliocene sea level was about 60 meters above present, with an uncertainty based on the uncertainty in the dynamic models of about 10 meters to 22 meters. And what that means, if you then recalibrate the ice sheet models using that new constraint, you end up with a much less extreme prediction of the Antarctic contribution to sea level rise by the end of the century. And so the good news is it suggests that the really extreme predictions of future sea level rise are actually less likely in light of this new constraint. And so finally, I just want to leave you with sort of some work I'm doing at the moment with Bob Myhill and Harriet Lau and John Nalaboff, where we're looking at transient viscosity in the mantle. So essentially viscosity, where the effective viscosity depends on the timescale of loading that you apply to the material. And so we're using kind of tomographic constraints and then lab-based experiments on different rock analogs, and how the transient viscosity varies as a function of, for example, forcing frequency and temperature. So essentially predict what viscosity is underneath Antarctica. And what we find is that, interestingly, if you incorporate the transient viscosity or the transient behavior in these regions, then the discrepancy between the viscosity you estimate from GPS observations, which are shown in the gray bars, and what you get from the actual predictions, which are shown in these histograms. So the red histograms are if you include transient viscosity, the blue histograms are if you don't. You can see that actually it looks like to reconcile the GPS observations with the kind of tomographically inferred viscosities, you need to incorporate this transient mechanism. So it looks like there is actually some observational estimate, some observational evidence that transient processes are being activated. And so kind of the next thing I want to do is work with Harriet, Bob and John to try and build this kind of transient rheology into Aspect to look at essentially if viscoelastic rebound is sort of accelerated by this transient rheology, and that the rate of rebound scales with the rate of ice loss, it might be a possible negative feedback on ice sheet retreats in the West Antarctic, because essentially if you rebound the bedrock fast enough, you can stop the grounding line from migrating inland potentially, and stop the West Antarctic ice sheet becoming highly unstable. Obviously, this is unmodeled behavior, so we have no idea whether it will turn out to be important or not, but it's definitely something worth investigating. So that's my kind of current main Aspect project, which I haven't got as far with as I'd like. But if anyone has any ideas and would like to contribute to that, I'm sure me, Harriet, Bob, John would all be happy to hear from you. Thank you.
All right. Very cool. So we have 14 minutes for questions, and then let me look at the program real quick. So then after that, we have a 30-minute break, and we start again at the top of the hour. So we're not short on time. So this would be the time for people to ask questions. To both Fred and Derek, for that matter. Julianne, please go ahead.
Yeah, I have a question for Fred. I found the talk really interesting, and so I wondered, so you say basically from your constraints, you would say the lowermost 200 kilometers of the LLSVPs are some sort of really chemically dense material, and that sort of height is also what you would get in geodynamic models if you have some material that stays there stable for a really long time. But then if you compare that to tomography, right? If you ask someone who does tomography, they would tell you, oh, the piles are really really high, much higher than those 200 kilometers. And so, right, does that mean sort of what's above the 200 kilometers and then sort of a few hundred kilometers above that? So, right, if that's just hot, I would expect it to just rise. And then in geodynamic models, you could get something like a fuzzy top where you sort of have a mixture between some dense material and some other material. I was wondering if your models can constrain sort of what you would have above those 200 kilometers.
Yeah, so there's definitely, so the two things I'll say is that, so in terms of what we're actually seeing in tomography, so there's definitely a slight problem with resolution where we're not exactly sure what the vertical extent of these is, especially in the mid-mantle, the seismic resolution gets quite poor. What I would say though is that, you can also get low VS from high temperatures. So it could be that, you do have overall relatively high temperatures sitting above these chemically dense areas. So actually, potentially they're not, the anomaly you'd see in the tomography is not just confined to that basal layer, but you will see it extending above that as well. What I would say, so there is definitely a trade-off between how dense you want to make that layer and how fuzzy the top is. So, potentially it could be, a bit of a kind of gradational boundary where there is some anomalous composition sort of sitting above that denser layer, and it could then be a bit sort of thicker. The problem is there's a kind of trade-off between how dense you want to make that material and whether it's actually stable and doesn't get re-entrained in the convection. So there is a kind of limit to how dispersed you can make that without it then just being kind of entrained and not actually remaining as a relatively stable structure. But yeah, I would say that this does not rule out the possibility there's A, significant topography on that basal layer, and B, there's a bit more of a gradational boundary to it.
Okay, thank you.
Menno.
Right. I have a question for Derek, right? Actually, two questions. First one is, well, what's the computational cost of Fastscape compared to running a normal model? And secondly, does it have any effect on this, like the stability, like Runke-Taylor effect, if you use Fastscape or like the other diffusion talked about, or just if it serves as it is?
Yes, so what is it? So the first question, well, okay, so the second question is that it definitely does have an effect for the drunken sailor. And so this is something where we had to actually include the free surface stabilization when we use Fastscape, and this seems to help and get rid of this effect. But yeah, it's definitely something that we needed to consider. And
is it worse than if you don't use Fastscape, or is it better?
If you didn't have any stabilization for either of them?
Well, do you need more stabilization if you use Fastscape, or do you need more stabilization if you don't use Fastscape and just the free surface as is?
Yeah, that's a tricky. I think it's probably a little bit better with Fastscape versus the free surface, because we were having with models, we didn't need the stabilization, but in subduction models, then there was the issue that you had to have the stabilization. And I didn't do subduction models with the free surface, so I'm not sure. Maybe that's the case where it worked with the rifts and not the subduction as well.
Okay. And the computational cost?
Yeah, so the computational, it really depends a lot. If you have everything in there, if there's one aspect or Fastscape time step per aspect time step, even if you're using all the different components, it's not too expensive, but it also depends a lot on how much more resolved you have Fastscape. So if it's a large 3D model and you're resolving it many times above it, it can become quite a bit. Like I think in those Rift models, it was up to about 25% of the runtime. And a lot of this is because it has to be run on one processor, which hopefully once it's with the C++ version that Mikkel's working on, this is a bit better. But like the subduction one I did, I think it was about 5% of the runtime. So there it's much better. So it can vary a lot.
All right, thanks.
Welcome.
Actually, we are looking the workshop together in the seminar room in GFZ. So I have a question.
Please go ahead anyway.
Yeah. So I have a question to Fred. You have said like the LLSVP can have 100 to 1,000 times more viscous in order to maintain the seismic tomography image. But if you consider a basal layer LLSVP at the core mantle boundary and you give enough time to make a pile shape, do you still need a higher viscosity LLSVP, or the density only, the higher density only would give that pile shape LLSVP if you don't have any higher viscosity increase?
Yeah, so that's a good question. So I haven't run, so in terms of these models, there's the aspect models that I'm showing, they are either run forward from the present day for just a few million years, or I'm using backwards advection models where I'm essentially going like time stepping backwards in time and reversing the flow. And so essentially these pile shapes are what I'm already prescribing. So I'm not kind of running a long simulation to get a pile shape emerging in a sort of dynamically self-consistent way. So I'm sort of already imposing the shape. So that there's a question, basically I can't answer, with the simulation I've run, I can't answer a question about whether you could get a shape that looked like that just with the density anomaly. I think there will always be some trade-off between, the densities and the viscosities in terms of how you can get there. What I would say though is that, in terms of the kind of constraints I'm using, so these relative sea level changes, and then also kind of the present day CFD topography, dynamic topography, geoid, it is very clear that at least sort of starting from like at least the present day state, if you actually do think these piles have that morphology, then then the only way you can get a kind of an optimal fit is by assuming they are also more viscous. But yeah, to your question about whether you need the viscosity to get them to look like piles in the first place, I can't answer that with the simulations I've run, I'm afraid. But it's an interesting question for sure.
Yeah, and do you think that 1,000 times is a bit more viscous? 10 to 100 is okay, or do you think 1,000 is also kind of a good approximation?
I think 1,000 is possible. So what I'd say as well, so these are chemical viscosity contrast. So actually the total viscosity contrast isn't as large because these are also hot. So there's a bit of kind of trade-off between the temperature making it less viscous and then the composition making it more viscous. So they end up with somewhere in the middle. But they do end up slightly more viscous overall. So it does sound like a very large chemical viscosity contrast, but there have been some lab experiments on, for example, so the reason why I said that, potentially it's something to do with differences in post-perovskite is that people have, based on kind of rock mechanics experiments, suggest that maybe post-perovskite is a factor, so 10 to the 2 to 10 to the 3 less viscous than perovskite. So if that's a phase that's really governing the rheology down there, then potentially these very extreme viscosity variations aren't completely nuts. But yeah, it is a good question. You would generally assume the LSVP is hotter, so you'd assume it have less post-perovskite in it, which might then help you to kind of get this contrast. I said as well that, you know, potentially it's chemically anomalous. It could be that it's just a weird composition that happens to be more viscous. But yeah, like which of those two, I'm not really sure.
Yeah, there is another question.
Yeah, it's just a follow-on question.
Hi, Badas.
Follow-on question. Since you were talking about the thermal viscosity contrast, so do you have any constraints on this, or what are your assumptions on how the viscosity depends on temperature in the lowermost mantle?
Yeah, so in those cases, the viscosity contrast is actually based mainly off kind of the Steinberger 2006 models in terms of looking at kind of scaling the experimental constraints into there. So the kind of the effective activation energy down there is about kind of 200 kilojoules per mole. I haven't played around very much with, you know, because obviously the rock mechanics experiments are quite variable in terms of exactly what the right parameters should be, both like activation volume wise and activation energy wise. And there will always be a bit of trade-off, I think, between the temperature dependence you assume and the chemical viscosity contrast. But I'd say the temperature dependence is relatively well constrained. So I chose to say that's the thing that I'm not going to vary. And then I'll change the kind of the chemical contrast. I mean, I have played around with it. In general, what I find is if you make the temperature dependence too low, then what happens is you get a very unstable boundary layer and the top of the mantle. And then you get all kinds of sort of very weird behavior where, you know, all the continents are sinking. There's like large things blobbing off the oceanic lithosphere, which it basically just ends up giving you poor fits to observational constraints. So essentially I could have tuned the temperature dependent viscosity to make sure that it could give me good fits to kind of present day constraints, and then kind of played around with the chemistry. But there's definitely going to be a trade-off between those two for sure.
Okay, thanks.
Thank you.
No worries.
Renee, you have your hand up.
Yeah, actually, I have questions for both of you. But since we talked with Fred right now, let me ask you. So you mentioned that you started with a kernel method to run your models and then switched later to aspect. Did you do any comparisons between the two results? Because I'd be curious how close they are.
They are. So they are very close, especially in terms of the dynamic topography. Things are not so good for the geoid, and that's because the kernels I was using include self-gravitation. An aspect so far doesn't. So, you know, you kind of get the same shape of geoid, you get the same pattern, and it's all pretty consistent, but the amplitude is slightly lower for the geoid. And also it seems to be slightly, the dynamic topography almost seems to be slightly the other way. So the dynamic topography amplitude seems to be slightly higher than you'd expect from the kernel method. So there are slight discrepancies, but I guess for me, what I'm sort of suggesting is that at least the kind of the trends in these changes, like the relative changes as you kind of move across models, those should be kind of preserved between the two. But you're right, the absolutes and components of the system, yeah, they do vary, especially the longest wavelengths because of the self-gravitation being in one and not the other.
Yeah. And a second question was, you mentioned that you computed the paleo sea level out of the data. Can you describe the workflow a bit? Because I know that we've been working on a post processor for a bit to do something like that, but it's not it's not ready. I think Maike Werdestein worked on that with
yeah. So the approach I'm taking is based on sort of Jackie Alston's work. So I was sort of taking the dynamic topography field, and essentially what I'm doing is I'm then sort of rotating that dynamic topography field according to the plate motions that have occurred since the Pliocene. And then there's a kind of iteration step where, because obviously if the dynamic topography changes the coastline position, then it also slightly changes the kind of water loading. So there's a solution of the sea level equation also going in, but it's all going to kind of calculate dynamic topography. I kind of run it through this kind of offline post processor to work out sort of essentially how the sea level varies in the reference frame of that shoreline deposit, and including the kind of full sea level equation. But
so it's essentially a post-processing step that you do outside of
outside of aspects at the moment.
Yeah.
It would be really cool to have it within,
yes,
and also more self-consistent, because I'm having all the kind of rotation of plates, and it's a bit fiddly and it's in MATLAB at the moment, which is not ideal. But yes, at the moment it's a separate step.
Yeah, would be a cool project to get it in. Thanks.
Definitely.
And to Derek, just briefly, you mentioned that in your equations that you showed for how the surface develops, you had continental sediment flux that moves from the continent into the ocean, and that's then deposited in the ocean. But can you describe how that is distributed in the ocean? Because I didn't quite see how Fastscape would know where it's distributed.
Yeah, that's a good question. Something actually I'm not too sure I can answer very well. There's a paper from Xiaoping 2019 that would go more into exactly how they decide it.
Okay.
And I think too, there's some small issue with it that I saw and had a pull request for on the Fastscape thing, that they might be overestimating the amount of sediment that's going in. But yeah, I would have to look further into it.
Okay, perfect. Can you maybe write down the paper that you mentioned in the chat, that just so that I have a reference?
Sure. Yeah, I can do that.
Cool. Thank you.
The multi-person Potsdam screen still has your hand up. Do you have more questions? But you're muted. You need to unmute yourself.
Yeah, so since Fred mentioned the geoid and the self-gravitation is not included, so that's something we've actually also been noticing. So basically, I was just wondering, maybe later on in the discussion, there's already plans to include the self-gravitation, because I think I have idea how to do it, but not within aspects. So I could do it as a post-processing, but if there are already people working on it within aspect, then this is something which I would be certainly interested in. But maybe we don't need to discuss this now, but later on in the discussion section. Thank you. Or do you have something to say about this right now, Fred?
We do have the time. I mean, we have a break. Everybody's free to go, but we can spend the next 25 minutes on chatting too.
Okay.
So go ahead, Fred.
I mean, so yeah, I mean, I agree that it'd be great to have it in there. I realize that it is complex, and there's different implementations you can use that might make the computational cost of running the simulation very prohibitively expensive, all the way through something a bit more simplified. But yeah, I think it's definitely something interesting. And I think at the hackathon I was at way back in sort of Utah in maybe it was like 2019, 2020. It was one of the things we were thinking about, and then I think everyone just kind of realized, oh, it's going to be too complicated, so it got dropped. But yeah, I'd definitely be interested in trying to kind of develop something like that, because there are the codes that have included self-gravitation. I'm aware, for example, like the SpecFem guys have tried to include self-gravitation in SpecFem, and there's a few other codes. Obviously, the difficulty with gravity is, you've kind of got this boundary condition at infinity that means how you kind of do kind of the solution on the kind of gravity mesh and the kind of actual Earth model mesh can get tricky, but there clearly are ways to do it. So yeah, it'd be interesting to have a look at.
Yeah, it's also, I think in SIPSCOM it's also included, and it works quite well. So it has been very well benchmarked with the spherical harmonic code, whereas whereas in aspect we've also tried this comparison, and we saw this difference. You can take out the self-gravitation from the spherical harmonic code, and then you get a very good agreement with the aspect. But with it, you obviously, as you mentioned, you get this different amplitude.
Yeah, maybe we should just copy sitcom. What they did.
I have a question for Derek, if there is time. Yeah, Derek, I really like your model of subduction with this formation of duplex. Have you tried varying like the friction of the sediments, the friction coefficient, to see if you will still, how big the duplex will become, how much sediments you will break down? Yeah, if you can switch from accretion to a subduction erosion, for example.
Yeah, so this is interesting. This is kind of what we want to start looking into, but again, it's still very early. I was just happy to get one model run for this presentation. What we're actually thinking of varying is we include a pore fluid pressure that's depth dependent in these and composition dependent. So for that specific model, our sediment went from pore fluid factor of 0.4 to 0.9 over 4 kilometers, which actually helps a lot to get these wedge structures to form. And so then we're going to eventually vary this to maybe 0.8 to 0.99 to see how this affects the subduction in the wedge.
Well, anybody else? I'll have one last question right then. My background is not in the geosciences, and so I come to meetings like the AGU, and I'm just curious what people figure out. And the question, of course, what the LLSVPs are, has been around at AGU for as long as I've come to AGU, and or as long as I've been in this community. And I think ultimately what it boils down to is the stuff is very deep in the earth, and it does not have a great effect on what we see on the earth, on all of the data that we have, right? And I mean, you showed this in one of your figures where you show, sort of the fit that and for different viscosities, and you say, well, this is the minimum. But the curve is really flat, right? And so you get slightly more misfit for an order magnitude difference in viscosity. And so if you were a gambling person and you had to sort of make a sealed bid that is going to be opened in 20 years, how much confidence do you actually have in sort of the conclusions that you have? This is not being critical, right? I mean, there's nothing that you can do about the data that you have. I'm just curious, sort of, how much money would you put on your conclusions?
So in terms of, you're quite right that in terms of as you vary the chemical viscosity contrast of that deep layer, it's a very flat minimum. So yeah, there's an optimal model, but it's not very well constrained minimum. So that part, I think, it's suggesting that there might be a more viscous layer down there, but I wouldn't want to bet my house on it. Especially because to really nail down what's going on down there, what we really want, if we could get any data set, it would be what is a CMB topography? And at the moment, depending on which method you use, the answers are all over the place. So it's not actually very helpful at the moment, apart from that very long wavelength 2.0 coefficient. So in terms of the viscosity part, yeah, I'm like less sure. In terms of the density structure, I'm more confident because basically every single different data set we seem to be looking at is pointing in the same direction. So you're right that each individual data set on its own is kind of like can't resolve it on its own. But if you look at the kind of the seismological evidence, so it's like how VSVP and bulk velocity will vary as a function of depth. You look at the geodynamic constraints, you look at things like Harriot's body tide work, and even to Paolo's Stoney modes kind of don't really help to constrain it that much. But there's some recent norm mode studies that are also pushing in that direction as well, that it's anomalously dense down there. I'd be pretty confident that there is some anomalously dense material down there. Like what it is exactly, kind of its exact thickness, I wouldn't want to bet my house on, but I do think there is definitely evidence that there's at least a thin layer of anomalous material down there. But yeah, if we had, CMB topography would really change the game if we had more than just the 2.0 harmonic. But at the moment, there's so much variation between models of CMB topography that, yeah, I wouldn't. They're kind of not useful at the moment.
This is something that I know nothing about, and so I'm just really curious. What is it about the CMB topography that's hard to get? Is it because
it's trade-off? So yeah, so the different measurements we have to constrain it, they're mainly seismological, so norm mode seismology, and also you can use kind of body waves to some extent. But the real problem is that there's so much trade-off between the SVP density CMB topography in those inversions that unless like you've got every single one of those really well constrained apart from the CMB topography, then the inferred CMB topography is very hard to get at, because actually the sensitivity to CMB topography is often smaller than it is to those other three components, so the SVP density. And so the issue is that you just don't have great sensitivity with the measurements we have, and there's so much trade-off. So different people get different answers, and I think it's mainly due to essentially, the fact that there's these different trade-offs and different people are assuming, they're fixing maybe VP structure and letting other things vary, or vice versa. And so I think that's the main problem at the moment.
That's interesting, because naively, I would have thought, well, there's not a stronger interface than between the core and the mantle, and so you get really strong reflections, and how hard can it be? But then I'm also the topography you expect are probably on the order of, a few hundred meters, maybe a couple kilometers. And so the travel time differences are really small, right? And that's probably part of it too, that you're not probing this with, 100 hertz frequencies. And so a few hundred meters or a couple kilometers really doesn't show up very much in seismograms.
Yeah. So it's difficult. I mean, one thing you can say though is that in general, so we know that the CMB topography has to be kind of on average slightly elevated above the LSVPs, otherwise you wouldn't get the right geoid signal. So there's some very broad things we can say for sure, even with what we have, and it's forgetting about the seismology for now. But yeah, I think you're right. It's partly, it's not a huge amount of topography given the measurements we actually have to deal with it, and also any seismic phases we're looking at have gone through all kinds of complexity on the way back up to the surface. So, it's hard to disentangle that. And then there's also just the fact that we also think that core mantle boundary region is potentially quite complex. So people have come up with all kinds of anomalous layers in the outside of the outer core, and sort of things like ULVZs and LSVPs on the mantle side. And so when you've got all these potential complexities as well that are kind of playing into it, it makes it a tricky problem. I want to sound more hopeful. I don't know, maybe if we have sort of more seismologists in the oceans, finally, we might be able to kind of start to disentangle some of these things. But yeah, for now, it is a bit complicated getting at CMB topography.
Yeah, I mean, so the statisticians have developed methods to give sort of a level of confidence to, you come up with two hypotheses, for example, right? And you want to say, well, this is the right hypothesis and this is the wrong hypothesis, and there are measures that you can apply. But they're, in order to compute them is just, out of this world, right? I mean, you would have to run Bayesian inversion schemes for the sort of stuff that you do, and it's just not feasible. And
no, I think we could potentially start to try and generate emulators. So we're never going to do like full physics informed neural network type things, I guess, for mantle convection simulation, especially with complex rheology. But one potential approach is basically coming up with essentially like a fancy regression model, a kind of an interpolation scheme to say, roughly what would you get if you had changed your parameter for some intermediate values, provided you've bounded the extremes. Can you kind of work out what it would be for some intermediate values? And then if you've got that rapid emulator, then you can do Bayesian sampling. Obviously, it's an emulator. It's not like the real simulation, but it might be accurate enough that you can get some idea of whether you're above or below resolution of a particular hypothesis. Maybe.
Good stuff. Julianne.
Oh yeah, that's something I just wanted to say, like, to this discussion. I mean, Wolfgang, of course, you're right. We've been talking about this for 20 years or more, but I feel we've also made progress, right? I feel in the beginning, everyone was talking about like, oh, are they thermal or are they thermochemical? And now we have these specific constraints like, oh, at this specific depth, what would the density contrast be, and uncertainties. And so I think, right, Fred's study also shows that it's really cool that it's not just looking at one observation, it's looking at all of these different observations. So I think, right, we might not have solved exactly what type of composition it is in 20 years, but maybe we're closer to, right, it has to be within this percentage of, I don't know, basaltic or primordial or whatever composition.
Yeah. I mean, I did not mean to dismiss, your talk and all of the evidence that you bring, right? I mean, there was a lot of data that you include in it. 20 years ago, I think the talks were of the sort, we think that we see something in seismic images, right? I mean,
I think the key going forward, and I think something that actually will allow us. So we've, Harriet's developed this new tidal tomography method. We've got kind of new null mode approaches, and like things like more people are using like full coupling of the null mode, so they're better constrained. So we have these new methods, and we have better seismic data all the time. The thing I think would be helpful is, so what we found with the Stony modes, for example, is, so the main difference between Howler's 2017 paper and what was in the Richards 2023 paper was that we included the actual kind of like dynamic CMB topography predicted by these sort of geodynamic models in the Stony mode inversion. So what Harriet did, what Paolo did initially was just assume that, like, whatever the density anomaly is down there, it's isostatically compensated at the core mantle boundary. So, and there was some scaling factor between density and CMB topography. Whereas in this case, we were using kind of dynamically self-consistent CMB topography in the Sony modes calculation, and that actually allowed us to get quite a different result actually to what Paula saw. And I think it helps you explain the observations better. So I think more integration of sort of geodynamic modeling and seismic modeling, I think can really help, because if everything is self-consistent, then it really does reduce the possibility for kind of these sort of slightly artificial discrepancies to arise, and potentially because you've got not just seismic data to look at, you've then got all these kind of geodynamic constraints you can use as well. They will all have trade-offs and there will all be some uncertainties, but the trade-offs might go in slightly different directions. So hopefully there's some point in the middle maybe where there is like a small parameter space that fits everything. But yeah, how we do that is to make sure that everything that the seismologists are doing is kind of consistent with what the geodynamic model is doing and vice versa. And that's kind of an interesting conversation. But I think, yeah, definitely integrating seismic and geodynamic constraints is very helpful. And this is not new. Alessandro Forte has been doing this for a very long time with Steve Grand, people like that. So a framework does exist, and I think there's definitely value in that.
All right, very cool. I'll propose we take the remaining 13 minutes of the break and then I think, let me look this up. So at the top of the hour, we start the next session, and Benno is going to chair it. Thanks to the two of you. Cool talks.
Thank you. Cheers.
Thanks.